So the next speaker will be Dankert Feist from the Ethereum Foundation.
Yeah, hello. I'm Dankert Feist. I do research at the Ethereum Foundation, and one of the things I'm looking into is sharding and data availability sampling. I will introduce the topic of data availability sampling today. I'll start coming from the starting point of like why we need this. So like what is sort of the blockchain scalability problem that we're trying to solve? Why is data availability something that features into this? How data availability sampling solves this? And for the particular interest of this workshop, I will be talking about the lazy node problem, which is like one of the interesting questions that maybe like it would be interesting to do some crypto economic analysis on. So the blockchain scalability trilemma is something formulated a few years ago by Vitalik Buterin, and basically he said that it's difficult to design a blockchain that provides at the same time scalability, security, and decentralization. And it's important to say here, like it's not impossible. Like actually, by now we know how to design such systems. It's just that the building blocks for that were not known at the time. So like around 2015 or so. There were still a lot of unknowns, and basically with the way that blockchains were designed at that point in time, it was deemed impossible. And so to understand this, we have to first talk about decentralization. So what does decentralization mean? And the important part is what I'm depicting here is the node that the user runs at home and the internet connection of that node. And that features very importantly in this. So like to us, decentralization means that everyone is able to run a blockchain node at home. And in particular, it means that this node is limited by two factors. One is execution. So this little machine that's like that you can buy that has a limited amount for a limited capacity for execution because it should be cheap. You shouldn't have to invest thousands of dollars into it. Ideally, it should be able to run just on your mobile phone. And also, most people can't easily get like a 10 gigabit internet connection or something like that. So like it should also be able to run with like a normal consumer internet connection. And so when we talk about the blockchain stack from a modern point of view, there's sort of four different components to it. There's the consensus part, which is like proof of stake or proof of work. How you come to consensus on what is the what is sort of the latest state of the blockchain you have to consider. There's data availability. How do you make sure that whatever the consensus has agreed on is actually available to everyone? There is settlement, which is basically what is the layer on which you settle financial transactions, and there's execution, which is about how you resolve transactions. How do you like agree on the latest on the actual result of the latest state? And there's basically two of these components that actually require scaling. So both consensus and settlement don't actually have to scale, because consensus in a way it can only be about a state root or something. So it's trivial, like it doesn't need scaling. And settlement can be reduced arbitrarily. Yeah? You don't need to settle every single transaction. You can settle in large batches. So that's not a bottleneck. But data availability and execution, those two, they need scaling. And for execution, for a few years now, we have known how to do this. Basically, there's a construction, or like one of the possible constructions, so-called rollups, which post all their data on chain and get the and assure the validity via either fraud proofs or validity proofs, or like what people call zero knowledge, where the zero knowledge property is not actually required here. So that's how we scale execution. And for data availability, in order to scale data availability, we need so-called data availability sampling. Okay, so let's talk about the data availability problem. So data availability for a blockchain means that no participant, including a colluding supermajority of the full nodes, has the ability to withhold data. So this is important. Like what we want to protect against here includes actually someone who has completely overtaken to the consensus. So this is important. Like this is why we build blockchains. We don't just want some consortium to agree this is what happens. We want everyone to be able to check this, and that means even if if whatever provides the consensus has turned evil, we want the validity properties to still hold. And the way we do that is that we protect even against colluding supermajorities. And the way current blockchains solve this, so like data availability for blockchains like current Ethereum or Bitcoin, isn't actually a problem. Like it's actually like trivially solved because all nodes just download all the data. So if I run an Ethereum node right now, then it will just continuously download all the blocks. And so I know they're available because otherwise I couldn't download them. But the problem is this is not scalable, because scalable means that the work required should be less than downloading all the blocks, because that is linear in the number of transactions that I want to post on the blockchain. So I want to reduce this to something less. So for example, reasonable would be a constant or a logarithmic amount of work. Because there's a lot of confusion around this, I want to like emphasize this a bit. So data availability, what it means is the assurance that data was not withheld or the assurance that data was published. What it is not is any statement about data storage or continued availability. So we separate these two things. Like it's not, I'm not saying like these are not important. Like yes, like I would want all data on a blockchain to be available forever. But you achieve that in a different way. Like the first important thing in order to make sure that data will be available forever is that it was available in the first place. So what we care about with data availability, and this is sort of like the difficult problem, is that at the point when a block first entered consensus, when it first entered the blockchain, it cannot be withheld. There cannot be someone who's like, the data was never published, but somehow it became part of the canonical history of the blockchain. This should never happen, basically. Cool. So how does data availability sampling work, and how does it solve this? So the idea is that we take our data, we split it into many different chunks, and we sample it. So we have a client who basically requests some random chunks from this data. But the problem is, if you do this naively, and one of these chunks is missing, you will probably not detect it, because it's unlikely that you request that particular chunks if you only sample like a few random ones. So basically, if you do just random sample on the raw data, this is not enough, because say you sample 10% of all the data, there's a single of the chunks that's unavailable, probability that you catch is 10%. And so that's not efficient. So you sample 10%, which is already a lot of data, and you only have a 10% probability of catching it. So we need a way to amplify this so that a small number of samples can already give us a very high probability that we catch catch this property that the data is not available. And so the way we do this is using so-called erasure coding. So what we do is, in this example, I use a Reed-Solomon code. So what you say is, you have some original data. This is these 4 first chunks. And what you do is you interpolate a polynomial through this data, and you evaluate that polynomial at, again, the same number of points. And so through these 4 points, you get a polynomial of degree 3, and then you evaluate it 4 more. And then because any polynomial of degree 3 can be interpolated using 4 points. It doesn't matter which 4 of these 8 points you have. You will always be able to reconstruct the exact same data. And so this is an example as given at so-called coding rate of 0.5. So that means you need 50%. You could make this different by giving more or less of these extension points. And what this means is that sampling becomes efficient, because if you, for example, query 30 random chunks, and let's assume someone wants to withhold data. In order to withhold data, I have to provide less than 50% of the data. Otherwise, I can't withhold it. If I give more than 50% to the network, they can get everything. And so what that means is that if I try to withhold it, then anyone who does the sampling is very, very likely to catch me, because one of those, like some of those 30 samples will not be available. The probability that all of them, in all of them, they will sample samples that I have made available is 2 to the minus 30, which is really low. And of course, I can make it arbitrarily low if I make this number higher. So yeah, this is how we get scalable data availability. And so what guarantees does this give us? So there are basically 2 different ways to see this. So the sort of naive model is that you say, like, okay, like whoever provides this data has to upload it into some networking data structure, and then all the nodes sample it from that data structure. And so each node gets like the statistical security that in a withholding attack, there's at most this 10 to the minus 9 probability that they will be tricked and that they accept something as available that is not. So it would be really nice if you could get that. Unfortunately, I think in most cases this is not a realistic model, because, as I said earlier, data availability sampling is about protecting us from even a colluding a colluding consensus majority. And so if someone is powerful enough to overtake your consensus, it is very unlikely that you will be able to protect your network from it. So like we actually have to assume that the attacker controls large parts of your network as well, and so you basically have to assume that the attacker can give you, like, can decide whether they give you a sample or whether they don't give it to you. And so what you actually, the probability you actually get is that they can always, like, if they in particular target you, they know, like, this is your node and I want to trick you into believing that this data is available, then I'll just give you all the samples. But I've only given you like a small number of samples, so that doesn't help the network reconstruct the data. So the probability you get instead is that as long as like most people sample, you can only trick a small number of nodes, like a finite number of nodes on the network. So like, for example, like let's say there are 10,000 samples per block and each node samples 100, then you cannot sample more than about 100 nodes. About 50 nodes, because if you do more, you would give more than 5,000 samples, and then like all the data would be available. So it would be like 0.5%. Cool. So these are the guarantees that data availability sampling can give us. And now I want to go a bit into like, what happens if nodes don't just do like what we tell them to, but they might behave rationally, which turns them into lazy nodes. So like this problem has been around forever, like it already exists even without data availability sampling. So basically you have to assume that validating a blockchain is in some sense expensive. Of course, we're trying as hard as possible to make it as cheap as possible, but it is an expense that the participants have to bear. And a rational participant might weigh that against the benefits. So basically, if I can assume that most other people run full nodes and validate the blockchain, then probably attacks are sufficiently discouraged. So I can get away with not doing it. I can get away with just trusting that everyone else does this, and probably like the cost of attacking just me is too high, and so like I'm still protected by all those other nodes. But this ceases being true if there are too many lazy nodes. So basically, at some point, you will have so many lazy nodes that now attacking the blockchain becomes profitable again, because now suddenly you can trick a lot of people into believing something that's incorrect. So basically, I try to illustrate this with this little diagram. So basically, you have some amount of capital that you have to burn into for an attack. So for example, if you do like a double spending attack or something, you will have to say, for example, on Ethereum, you would have to finalize, if you have to finalize 2 blocks, then you would like get a large number of validators slashed, and so you would burn an amount of capital. So you have something that's some cost to execute this attack, and then you have basically like transactions or like value protected by validating nodes and lazy nodes. And as long as the capital that you have to burn for the attack is larger than what you can get from the lazy nodes, everything's fine, and the attack is not worth it, and it's discouraged. And of course, like once too many nodes become lazy and they exceed the threshold, then at some point the attacks become worth it, and now like you're in trouble, and it's worth attacking the chain. So basically, like very roughly, like we expect that like sort of expectation neutral nodes will validate the blockchain if the cost to like validate the chain is less than the expected cost to them of an attack, which is the probability of a successful attack times the potential loss. And this is a very simplified formula, because it only holds if validation fully protects a node from an attack. For data availability sampling, it becomes a bit more interesting. So our game will have several more potential outcomes, because we do also get this property that an attacker can trick a limited number of nodes. But you also get a potential, like instead of just sampling, you can also download all the data. So we have several different actors. We can now have nodes that download all the data and are perfectly protected, nodes that do data availability sampling, and lazy nodes that do nothing. And so basically, I try to roughly like illustrate the potential outcomes of this game here. Like you can have like fully downloading nodes that can never be attacked, sampling nodes and non-sampling nodes, and then you can have the probability that you have no attack. You can have a general withholding attack where like someone tries to withhold data from the full network. You can have targeted attacks that concern a particular node or concern me, like if this is my matrix, my payout matrix, and I can have a targeted attack that concerns others, but that might still affect me in that like I am accidentally following the wrong chain, for example. And so yeah, this is basically like if I download everything, then I get the cost of downloading everything, but in all of these attacks, like I'm unaffected, nothing happens to me. If I do data availability sampling, then I have like a much lower cost, but I can be subject to a targeted attack. So like I could be the victim if someone in particular wants to trick me. And if I do no sampling, then I can be a victim in both a general withholding and a targeted attack. And also if someone tries to target someone else, then I may still follow the wrong chain, which might still have some cost to me. So like I would be collateral damage in that attack, although it's probably not specific to me. Yeah, so I think like this is kind of my input to this crypto economics workshop. Like if someone wants to like look into this game, I think it's interesting to look at what the different the incentives are and what the full payout matrix is for this game of like potential lazy nodes and data availability sampling. Cool, thank you, and yeah, I'm open to questions. So what do you mean by outsourcing? Yeah. Huh? You want? Sorry, like I'm not sure. What do you mean by outsourcing? Like. Yeah. I mean,
I had maybe a related question.
Yeah.
On that previous slide.
Yeah. Mm-hmm.
So who makes the decisions? I don't know if this is a similar question or not.
Mm.
Usually nodes independently decide which column they want to be in.
Yeah, so you can decide that yourself, right? When you set up a node, you would decide. I mean, of course, we would not design our software so that it allows you to just select no sampling, but you could modify your own software because you say this is too expensive for me. Yeah.
Do you feel like the protocol should in some ways incentivizing people to make good choices?
This is the tricky part because these are full nodes, right? So these are not in like it's not a validator. A validator you can incentivize to do something. You can pay them to like say compute a proof of custody, but these are just the nodes that you run at home, and they're the only way we might not know about it at all that you run this node, right? So we don't really have a way of paying you to do something. Sorry, like so the outsourcing question, like I mean, it's a bit confusing to me because like it sounds like you're just yeah, you're basically if you outsource it, then you're more or less in the no sampling like column because you basically just you're not validating the blockchain yourself. You're just like trying to get someone else to do it for you, and that means you just trust them to like, and they could do whatever to you. Yeah. So yeah.
Are there any like case studies or active systems going to open peer-to-peer networks that leverage data availability sampling across like multiple nodes, like a torrent times or torrent network or something like that?
So this is very different because torrent does not do data availability sampling, right? Torrent. Sorry. Yeah, so he's asking whether there are live networks that do data availability sampling, and so I think like there are. I think like Celestia probably has like test networks at the moment. That's the only blockchain I'm aware of. But like all other systems, like the data availability problem is not like all other systems. What they want to do is storage instead of data availability, which is like a very different problem.
Yeah, just had a follow-up. I was just wondering what are the synchrony assumptions with the continuity sampling?
No, you can in principle do this at any time. What you want is that like basically all the blockchain clients do this at some point when they synchronize to the chain, but they wouldn't have to do it at the same time.
Is that potentially a fourth strategy here where you could see if a block has a potential to target you and then selectively choose the block's available?
So the question is whether you could look ahead whether the block could target you and then choose whether you validate. So I mean, naively, not obviously so, because if you don't download any data, you wouldn't know what the block does anyway. But I guess you could potentially, I mean, I have never thought about this, but like if you think about, you could ask someone to like construct a proof that the block contains no transactions that affect you, and then you could decide based on that whether you should sample or not. I don't know if that makes any sense, but yeah, you could think about that. Yeah.
So if I'm sampling, I can't prove to others though that the person I'm sampling has failed, right?
No.
So in that case, what was the point if I can't sort of prove to them like, hey, this person's not, it's also not sure.
So the theory, like, what should happen is. Okay, so the question is, you cannot prove to someone else that that your sampling has failed, and so the question is, like, what's the point of data availability sampling then? And the idea, so yes, so it is data availability sampling is subjective, but okay, so except for the case where someone fools a small number of nodes, in all other cases the protocol should converge. So either at some point. Either everyone should fail the sampling because there was less than 50% of the samples available, or eventually all samples should be available, because if more than 50% were available, then you can reconstruct the full data, reseed the table, and then everyone would see, oh yes, it is actually available. So that's the convergence property. Yep.
All right, great. Thank you. Next speaker back, Ansgar Dietrichs from the Ethereum Foundation.
Yeah, hey everyone. My name is Ansgar, and I'm here to talk a little bit about multidimensional resource pricing, which has been a topic that we've been looking into a little bit over the last year. So I kind of structured it in two parts. First, the why, kind of what's the more the abstract theoretical side of it, and then the kind of the how specifically in the Ethereum case could we bring that to our chain. So on the why side, the first few slides are from a more general audience kind of talk, so it's a little kind of high level. I'll go over them quickly, but basically the idea is just when you look at an Ethereum transaction, on the left side there's just a screenshot of a Etherscan Ethereum transaction. You see down at the bottom kind of the resource usage, the kind of the cost that the transaction had to pay for, and a lot of people start with the intuition that basically the money they spend on a transaction basically goes for paying for the kind of directly paying for the effort that you cause, and of course that's not quite right for Ethereum. The actual kind of reimbursing someone for their direct effort, the only part that goes to that is this what we call the priority fee. So that's just like a small tip that you give to the miner for the effort of inclusion. The main part of the fee, so in this case, you can see we measure this in Gwei, which is a relative measure of Ether, and that's 50. So that's like a 96% of the transaction fee was the main fee, and that's really just a congestion pricing measure. So all we want to do there is just efficiently allocate a fixed supply resource. And basically, what is that fixed supply resource? Well, this is a little kind of diagram that I drew up like last year when we had this ERP 1559 update, and that was basically the situation before the update. So you can see that like the details don't really matter, but you can see that the supply curve is not really a curve; it's just like a vertical line, because no matter the demand level, unless we have like this, we are like below this cost offset demand level. We basically always want to fill blocks. That was before the 1559 update, but even after this update, now basically our supply cap, our hard cap has doubled, but still same situation. We have like a fixed price, and at that price, we basically just we are willing to fill the entire box. So it's just a congestion pricing situation. So when I say fixed supply of what basically is the question, right? So if we look back at the transaction. The cost that the transaction has to pay for is measured in what we call gas. In this case, the transaction used 46,000 gas, and so basically the idea, the idea basically is like what does gas stand for? So if we look at what's the underlying kind of things the transaction has to pay for, that's just a bunch of these. If you're not that familiar with the Ethereum system, you don't have to really know what any of these mean, but the idea is just the transaction has some static part that it pays for. It's a signature, it's the data that you send with the transaction, and some dynamic that are metered during execution. That's the virtual machine opcodes, that's memory, that's the calls it makes, these kind of things. How exactly do these contribute to the overall kind of gas cost? Like why is a signature? How many kilobytes of data is a signature worth? Basically, like how does this all map to one dimension? And for that, basically, the way we think about it is we go to like one level kind of higher in the abstraction, and we think of like not what are the exact operations you pay for, but what is the underlying resources you consume with those. And so this is just like one kind of shot of trying to come up with like a rough outline of the types of resources we're talking here about. So that would be something like bandwidth, right? That's something that, say, the data you send with the transaction directly contributes to, but say the signature doesn't, right? Because the signature is, well, it has a fixed size, but the actual effort is mainly the valuation of the signatures that would be compute. Then we have state access, memory, state growth, history growth. So just a bunch of different things that cause effort for the nodes in the network. And so how does that relate to our fixed supply? Why is there fixed supply? Well, the way we think about it on a network is that we basically, our main priority is the health of the network. So we basically, for each of these dimensions, resources, we pick a maximum worst case kind of throughput that we can sustain. Like, for example, right now Ethereum, you can create a block that would be up to 2 megabytes in size. We are confident that the network can handle that, but that would basically consume all the gas just for data, right? And you just can't go higher. And so for each of these dimensions, we basically just picked the threshold that we were comfortable with, and then we mapped that all back to the relative gas prices. Basically, what if a block only consumes this one resource? Like, how highly does it have to be priced relative to the others? And that's kind of how our gas cost originally happened. And just, if you're like an archaeologist of blockchains, that's actually quite a fun document to look at. That was basically in the very early days of Ethereum, before mainnet launch. That's where people basically literally manually went in and just tabulated all these different dimensions and assigned costs to the individual operations. So this is kind of the model we have today on Ethereum. What is kind of the problem? What are the consequences of this model? Well, one of the interesting ones to think about is just that right now, kind of the way we actually we combine cost of different resources is in this additive model. So in this scenario, basically, we just look at two resources. So that could be something like bandwidth and compute. And right now, those are basically competing for overall block space, right? So you can see you could say create a block that is full of data, so that would be a 2 megabyte block, but then you couldn't really do any compute, or you can have a block that does a lot of compute, but then you couldn't fit any data in, right? That just basically is a natural consequence out of this one-dimensional gas, because that's the only way we can really ensure that in the worst case, each resource does not violate its bounds. But is this a property we want, or is it a property we don't want? Well, if we look at the kind of the table of resources again, many of these resources are just completely independent of each other, right? So say the compute and the history growth, those are two completely separate concerns. History growth is about the disk space required by nodes in the network. The compute is about the kind of what kind of CPU do we expect them to have. Those two are just not competing. So if a block contributes to history growth, it doesn't mean that it shouldn't be allowed to contribute to compute, right? So what that means is we're kind of leaving resources on the table, leaving efficiency on the table. And what we would want, in this scenario at least, would be this kind of independent research usage model, where we would basically go from the kind of solid line to the dashed line, where basically you could consume up to the supply limit of resource A, but then also in the same block up to the limit, and it would basically no longer be competing. So that's basically one alternative pricing model that could fit some of the resources. The problem here is just in general that kind of all of these assumptions about how the individual resources relate to each other, they are all, of course, always simplifications. Not all resources are completely independent. And they in general have interesting patterns to them. So if we just look at this picture a bit more, one interesting kind of pattern that you can detect is that there are different types of limits. So the first few here, the blue ones are what we call burst limits. So those are actually like limits that are purely kind of relevant per block, right? So the bandwidth to compute, this is about how long does it take for a block to be propagated and validated in the network. But then the other ones, the orange ones here, those are like a fundamentally different type of resource, because those, like, we don't really care what an individual block contributes to whatever you need to hold on disk. It is about kind of the sustained, like, accumulated load over time. So these are sustained limits. And an interesting kind of tidbit here, if you stare at this a little longer, as we usually do, you realize that there's some sort of pattern where a lot of these kind of sustained limits roughly correspond to the burst limits. So say bandwidth, that's about like how big are the blocks, and then the blocks are stored, so that's the history that we kind of store. So that's kind of those relate. We have state access, which then again, like if you write to a new state, you cause state growth. But you can also see in this example immediately that this is also like a slightly messy model, because say state access can also just be a read, and a read does not contribute to state growth, right? So those are not like equivalent, they are just like related. So again, the point here is just to basically say that kind of like scoping out the kind of the resource landscape for Ethereum, coming up with a model for this is kind of like a non-trivial task. So kind of where we're at with that right now, and again, we only like started looking into this again a little bit this year, and it's more of an on-off thing, but kind of for now, we have these different models. It's like we can have additive resources that basically compete for consumption, or should compete, and we could have independent. We have this burst sustained relationship. There could be even more complex ones, of course, and again, the underlying reality is always more complex. The question is just what kind of simplifying model would we want to use. So the original kind of model on Ethereum that was purely additive. Now with ERP-5059, I kind of glanced over that a little bit. It's not too important for this talk, but if you know the mechanics of this, of how that works nowadays, where we have this, we have like a limit, but we also have a target that already has this kind of burst sustain characteristic a little bit, because we kind of set the target to limit our sustain limited resources, and then we set the hard limit basically for the burst protections. And then we could have something like a multi-dimensional variant of that, which would still have this burst sustain pattern, because we need that in general, also just for how this mechanism works, of basically always having real-time feedback of the kind of demand level of the system. But we could have the individual dimensions in there be for example, independent, or have a more complex relationship that still makes more efficient use of the different dimensions. The one additional little kind of detail here is that not only is it like a hard question to figure out to model the exact relationship between the resources in an efficient way, but it's also like already just the prior step of actually just coming up with the individual dimensions initially is one that quite strongly influences the kind of the outcome of the model. So if we look back at the picture, for example. So say in this picture on the compute side, we don't have a sustained limit, but some people can argue that whenever you connect to the network and for the first time, you sync, you basically have to process old blocks. That also is a cost, right? Like the more compute you have to spend at that moment in time, basically the slower sync is, and you could also basically want to have a limit on there. So that would be an additional entry here. Another point would be like some people look at this and they argue basically this picture heavily implies that like on the up-down axis, the resources are independent, but then they're actually really not, because say bandwidth and compute, both of those actually, if you wanted to go even one level higher, could be mapped to the same resource propagation time, right? Because propagation time means you have to download the block and you have to execute it, so it doesn't really matter whether it's bandwidth, you're waiting for the block, or then it's compute, you actually execute the block. It should be the same higher level resource, right? So basically, kind of even just the assumptions of the model just pretty heavily kind of influence the outcome there. And then, I don't know, I just threw that on here as well, just, given that it's kind of a academic style conference, is like, of course, there's been a lot of prior work in economics on different types of goods, different types of resources. We've been talking a little bit to different academics in the field, and it's really interesting to basically see to what extent does kind of prior do existing models kind of map to our scenario. Of course, it's somewhat kind of unusual with the kind of the fixed supply situation and everything. So it's not obvious that there's just like something off the shelf that completely fits, but it's like also like a really interesting question. So basically all this was on this side, just basically saying this is like an open research area, and we're like still at the relative beginning of exploring this. And then basically kind of coming out of this as like an overview of the theory side of things, just wanted to briefly also talk about how is this relevant for Ethereum specifically. I think this is like the shorter part. So the how. So starting, we had kind of what kind of brought out the topic again at the beginning of this year was a research article by Vitalik, January 5th, kind of outlining these ideas a little bit. Also already proposing a specific mechanism that we could use to basically bring this to the existing Ethereum ecosystem, or the blockchain. The problem there is that several problems. So first of all, as I was talking earlier about, like choice of model, actually kind of modeling the resources and the relationship really do matter, and any of these models will always have some error, right? They don't fit the underlying reality perfectly, and depending on what type of error you end up going with, that has different consequences in terms of like the failure cases that then your system has, and you have to be really careful. Right now, basically, our failure case of the additive model is just that we leave resources on the table, which is unfortunate, but it's safe. But if you say do the other thing, you go with a fully independent model, but it turns out that actually for processing time, for propagation time, it's still additive. In reality, then it might be that your network stability goes down, right? So actually, you have to understand exactly how does your model basically simplify reality, and what kind of failure cases does this introduce. So the first one, the choice, is a really kind of crucial one already. And then the other one, that's something that, I don't know, we unfortunately spend like a lot of our time just thinking on, and it's a bit annoying, but you can't help it. Just backward compatibility. We have an existing system running. It makes a lot of assumptions about one-dimensional gas. It's just not obvious that there is a good way of bringing it over to a multidimensional world without breaking everything, both on-chain in terms of the actual, the smart contracts we use on Ethereum, but then also off-chain tooling, UX, all these kind of things. It's a bit of a headache. And then the other one that's also just in practical terms really important, the effort required. On Ethereum, we have like a relatively bottlenecked kind of innovation mechanism, because of course we have this governance process. We need everyone to agree on changes. We need everyone to actually then develop these changes. So there's just basically kind of future roadmap changes are just also a very limited resource, and it's not obvious that we want to spend it on this. So basically bringing like the entire existing system over to a multidimensional world, it's unclear whether that's feasible. But, and I just wanted to already put that on there, because we've seen recently more and more kind of these newer chains, some with their own virtual machines, some just taking the EVM, modifying it slightly. I think for those, it would be just because if you can start from this blank slate anyway, you might as well go with like a more sophisticated mechanism, right? So I'd really want to see a little bit more experimentation, innovation there. Of course, some do, so I'm not doing, but like, I'd heavily encourage that as well. And then kind of as a last point here before I come to a close, basically if it might be infeasible to kind of go to a full-blown multi-dimensional system on Ethereum, is there anything we can do? And it turns out there is. So as like a case study, I just wanted to talk about one new feature in particular, and what is the benefit of new features? Well, the nice thing is that it's more limited in scope. You're not actually introducing 5 new dimensions. It's just like some small change. You don't have backward compatibility concerns because it's a new feature, and it is an existing roadmap item, so people already have to pay attention, have to put in the effort, so you might as well piggyback off of that and, add a little kind of interesting fee mechanism to that, so that it's just more practical. And right now on Ethereum, we are relatively close to bringing a new change to the chain that would, for the very first time, make Ethereum like pricing actually multidimensional, or two-dimensional in this case, which I guess is the most boring version of multi-dimensional. And that's the ERP for 844. So kind of both Dankrad, who talked about kind of the danksharding ideas just now, and kind of a bunch of us, we basically came up with this. What you could call it a budget danksharding. So it's like basically it takes this idea of trying to scale Ethereum, but for now it doesn't do any of the actual technical magic. So there's no sampling or nothing going on. You still just attach data to blocks, and everyone has to download them. So there's no technological innovation at all. So where is the innovation in this ERP? Well, basically what we would do is we would basically just say, if we just talk about pure data, which of these resources are affected, it's basically just bandwidth and history growth. And so we just manually kind of try to come up with a mechanism there that helps there. And in particular with history growth, we just have data that is only stored for a fixed amount of time, in our case 1 month. So basically it only has a fixed extra overhead, so we just ignore that. It's fine. People, we just don't care that much. And then on the bandwidth side, that's really interesting. That's how it ties back to multidimensional resource pricing. We basically just go to these kind of this independent model for our 2 dimensions here. We basically introduce a new dimension. This is just like a screenshot from the EIP. You can look it up, and I'll put the slides, I don't know, on Twitter or something. So if you want to have a look afterwards, you can find me there and find the slides. But basically, what it says right at the top is just we introduce data gas as a new type of gas. It's independent, and that's right the important keyword here, of normal gas, and follows its own targeting rule similar to 1559. So basically, this entire EIP is just a fee market efficiency trick. It's basically just, we add a second dimension, we get this efficiency gains. Of course, we accept, again, that our model, in our case, we just know our model assumes independence of the resources. That's not quite true, right? It's actually extra data. We already have data, so it does put an extra strain on bandwidth, but we understand kind of the inefficiency of the model, in this case, that it kind of doesn't account for that, and we just basically set our limits conservatively enough that it does not cause any problems. But basically that's it. So whenever you might kind of hear in the world EIP 4844, you should think, oh, interesting. It's basically just going two-dimensional, getting some efficiency out of there, while we actually do the actual sampling, networking magic in the background, and hopefully are ready with that soon as well. And so that's, I think, is basically just an example for a pragmatic way forward for Ethereum specifically, where we can basically use this kind of multi-dimensional model to inform these new features and get like small efficiency gains on the way. And with that, that was all from my side. Thanks. And I'm not sure if we have time for questions or what the situation is. Right. Yeah, this is a good question. Yes. So basically, the question was whether the kind of the validating the relationship between resources, say, kind of assumptions about independence, whether it's something that would be kind of suitable for simulation, or just these types of validation. And I think to some extent yes, but as I was saying basically earlier, where say, for example, just the choice of resource, the models that fall out are very sensitive to this. And I think the same would be true with simulation, where basically whenever you make simplifying assumptions, which you just have to do for simulations, basically the specific assumptions you make will be like very, like the outcome of the simulation will be very sensitive to that. And so I think what we do more and more these days also is just like real world testing, test nets, these kind of things. And maybe you could go like most of the way with simulations, but I think kind of real world testing will always be just like has to be a crucial part of that. Yeah.
I haven't specifically gone through 4844's EIP, but I just wanted to ask, is the TX type, is it going to be designated as free, like for the block transaction?
Where are we at? Do we have 012 already? Then I guess it should be 3. Well, we have legacy transactions, we have 1559 transactions, and access list transactions, right? So I assume it's 3, but I would have to pull up the IP, unless someone else here remembers off the top of their head. But I assume it should be 3 then, yeah. Any further questions?
So I wanted to make sure I understood the interaction with 4844. So should I think of it as like there's kind of 2 independent copies, the 1559 running, and like one on gas and one on raw data? So you have like a target and bytes on the raw data, and a target and gas on the.
That's right. So it's 2 completely independent mechanisms, and we initially wanted to set the target directly in bytes. We since kind of added one more layer of indirection just for kind of standardization. So we now account with something what we call data gas, but 1 data gas equals 1 byte. So it's and then we set the target in data gas. But yeah, it's basically the 2 of them don't know about each other basically.
And one other question. So if for the pre-4844 stuff, just the EVM stuff, if I gave you 2 dimensions, then you split gas into 2, do you know what you do?
I think that might be something like the kind of the state versus everything else, probably, just because state is just such an issue for Ethereum. all the time. So I think kind of having that cleanly separated would be like state access, state growth, all these kind of things. Basically, have a separate dimension for that. I think that would be my choice. Right. So yeah, we I actually happen to also have been a kind of part of the group that looked into state expiry like a year or so ago. Yeah. So basically, so there are two different types of expiry that we're looking into on Ethereum. The one, so maybe if we go back to here, one of them is history expiry, and that's kind of EIP 4.4 or 4.4.4 if you want to look it up. And that is actively being worked on. That will come to Ethereum, but that's basically a relatively simple one. All it does is say that nodes, for now, they have to store the entire history of the chain. At some point, we just say, discard blocks that are older than a year. So that helps with history growth. The much more intricate version of this is trying to basically solve state growth. And so there you actually look at the state, the current state of the chain. And you say, okay, if a certain account has not been touched in a year or two or something, everyone just forgets about it, but you still have it as part of your kind of state commitment. And then basically, if someone wanted to access it again, they would have to actually bring like a witness, a proof that is the current state. So you kind of shift the responsibility. We have a more or less working solution for that. Well, not implemented, but specified, mostly specified. It is unclear whether we actually want to move forward with it on Ethereum. It's a similar situation where I would hope that new networks start with it from the beginning, because then it's much easier. Most of them just haven't thought about this yet because they haven't run into the problem yet. For us, just the kind of the backward compatibility issues are so big that we might just never do it. If we were to do it, though, that just basically would mean that state growth, we would still need a sustained limit, though, right? Because if we say, I don't know, we want people to at most have to store 1 terabyte of state, and state is only kept around for a year while it's touched, we would still basically have to have some sort of floating pricing for state access to always target the kind of the size of the currently active state to be a specific size. But it would be a very different nature now than it is today. Okay, in the back. Right. So I think full multidimensional pricing, I haven't really heard any layer 2 looking into it too actively. I think right now, at least, the trend was that they try to be more and more equivalent to layer 1. So for now, they're kind of reluctant to do their own thing. And I think to some extent that's justified, because if everyone does their own flavor of multidimensional pricing, then at some point it's completely infeasible for wallet software and whatnot to support all of them. So for now, the answer there is kind of no for full multidimensional pricing. One thing that they actually, and I didn't mention it in this talk, but it's actually really interesting, is that layer 2s today on Ethereum are basically already forced to in practice do 2-dimensional pricing, even though there is no mechanism yet for it, just because if I send a transaction on layer 2, I pay for the layer 2 resources, right, the compute of the layer 2 nodes, the data and everything, but then they take the transaction and commit to it on layer 1, and usually that means they actually put the data on layer 1, and that's really expensive as well. So what they all started with is just like a 1-dimensional price, then they realized these two move so wildly against each other that it just really doesn't make sense to have those be 1 dimension. So right now they just all have a special handling, hacky 2-dimensional solution. And the hope is actually that they would be able to just take this EIP which introduces the new transaction type 3 or whatever, kind of with a 2-dimensional a preference and price preference expressed by the user, and basically would be able to adopt that as their standard transaction type, of course, where they interpret the second dimension not as a blob payment, but as a layer 1 commitment payment. But that, I think, would be a big help, because then you could have standardized support in all the wallets, and it would make layer 2 UX much easier. But this is also part of why actually this topic came up, because layer 2s already today, they're forced to deal with this.
What do you think about Solana's approximation of this problem with their account-based fee?
Yeah, that's a really good question, actually. I think Oh, yeah. So the question is, Solana, they have a kind of per account state access fee model. So so there might be like a really high price to access a state that's in high demand, and some other state that only you want to use that would be really cheap. So in their model, basically every single piece of state is its own dimension in a way. I think that's really interesting. So we have been looking at things like that as well in the context of, say, transaction parallelization, where you would want to basically, you can't really parallelize transactions that access the same state, so that would have to be more expensive. I would say, though, that kind of getting the details right there matters a lot. So I would say that basically these kind of approaches for now are mostly kind of in the experimentation stage. But I think, yeah, as a general direction, it's a promising approach, even though it's not clear whether, the complexity is worth it. Okay. Thank you.